still working.
Okay, we're ready to go.
Okay.
Okay, so today we'll have presentation by Nuria Miret Roig. She did her master's thesis at University of Barcelona. Then she did a PhD thesis at University of Bordeaux, for which she got the award for best PhD thesis in observational astrophysics by European Astronomical Society. She studied objects in Upper Scorpii and in Ophiuchus star-forming regions, and discovered not only stars, but also planets, many of them. So today she will tell us about origin of free-floating planets. The floor is yours.
Okay, so thank you very much for this kind introduction. I hope you can hear me well. In the room, it's fine, right, the sound? Okay.
Yeah, it's good. It's good.
Good. So, and also thank you very much for inviting me to give this presentation today at the University of Warsaw. It's my pleasure to be here with you today. And indeed, I will be talking today about the origin of free-floating planets. Okay, so this is the outline of the talk. I have divided it in three main parts. First, I will explain what I mean by free-floating planets. I will give a brief definition. Then I will address how can we detect them. And finally, we will discuss how can we learn about their origin and their formation mechanisms. So let's start already with the first questions. What are free-floating planets? So this might look, in fact, as a trivial introductory question, but in fact, we will soon see that the definition on its own of this type of object is a rather controversial and debated one. And in fact, there are two main categories in which free-floating planets can be defined or classified. The first one is according to their mass, and the second is according to their formation mechanism. Let's start with the mass. And here, almost everyone agrees how to distinguish stars from substellar objects. Star is an object that has a mass large enough, typically more than 80 times the mass of our Jupiter. And so such massive bodies can have high enough temperatures on the internal cores so that they can sustain hydrogen nuclear reactions for a long period of time. Then these stars sit in the main sequence for many, many years, millions or even giga years, and their stellar evolution is in a steady state for a long period of time. This is what characterizes stars. On the contrary, brown dwarfs and planets don't have enough mass to hold hydrogen reactions, and this is what we call the hydrogen burning limit. And then their stellar evolution, their life, is conditioned by this eternal contraction, because these nuclear reactions cannot stop and prevent gravity of slowly contracting. And they have a completely different stellar evolution. So this is why this hydrogen burning limit is an important distinction between stars and substellar objects. Then there is a second boundary, this deuterium burning limit at around 13 times the mass of our Jupiter, which distinguishes brown dwarfs from free-floating planets. Here, the difference is that brown dwarfs can hold certain types of nuclear reactions. For instance, they can burn deuterium or lithium at certain periods of their lives, while planets cannot hold any type of nuclear reactions. But then there are some scientists who argue that this deuterium burning limit has no strong impact on the stellar evolution of brown dwarfs and free-floating planets, and therefore they have proposed an alternative classification. In this other scenario, we can distinguish between objects that form by a direct collapse of a small cloud of gas. For instance, they would form similar to low-mass stars. And on the other side, we would have objects that form similar to exoplanets in planetary systems around a star. And then, for a reason or another, they can be ejected from this system and become free-floating planets. And these are the two definitions I was just presenting. So free-floating planets can either be these isolated objects that have less than 13 times the mass of our Jupiter, or we can define them as objects that are formed in planetary systems that later abandon. So I think this second definition has many advantages in the understanding of the nature of these free-floating planets. However, it poses some practical difficulties, since at the moment we are observing one of such objects, it's impossible to know which was the mechanisms that formed this object, right? So only for simplicity, I think the first definition in terms of mass is much more applicable, at least at the time being. So far in this talk, whenever I will be mentioning free-floating planets, I will be referring to objects that simply have less than 13 times the mass of our Jupiter, but we don't know by which mechanisms they were formed. Also, just to illustrate a bit of the controversy about these objects, we don't even agree on the term to name them, and also alternative names have been suggested in the literature. For instance, here you have some examples. So brown dwarf, isolated planetary mass objects, rock planets, etc. I think free-floating planets is the most used lately, but just so you know that all these terms also refer in principle to the same type of objects that I'm talking about. Fine, so these free-floating planets and brown dwarfs, I have widely given two main formation mechanisms, but if we look a bit more in detail, we will see that there are even a few more. So first of all, they can form in planetary systems, as I was describing. So similar to exoplanets, where the planet is orbiting a star, and then because the planet passes very close to another planet, or a star passes close to the planetary system, one of the planets can be dynamically unstable and eventually leave the planetary system. And this object will become one of these free-floating planets. Then it's also possible that they form like low-mass stars from the direct collapse of a small cloud of gas. This would be the star-like formation mechanism. Then we can also think of this scenario where several cores are accreting mass from the same gas reservoir. And due to dynamical interactions between the different cores, some of them can be ejected from the gas reservoir, and these cores will eventually not have enough mass to accrete to become stars, and they can become brown dwarfs or free-floating planets depending on the final mass of the core. And finally, also in the vicinity of very hot massive stars, the stellar winds of these OB-type stars can evaporate the outer layers of an accreting core, and then this core again will not have enough mass to become a star, and depending on the final mass will be a free-floating planet or a brown dwarf. So now we know that all these mechanisms do form free-floating planets and brown dwarf, and really the question is, which is the mechanism that dominates, or if several are at play, so which are the proportions of these different mechanisms? For instance, we know that photoevaporation and photodissociation, this is a mechanism that has been proved to happen, but since it can only take place very close to hot stars, which are rare, then we know that this is not the dominant mechanism of forming free-floating planets. And same would happen with the rest of mechanisms. So we want to know really which are the most important ones, or maybe at different masses, the importance of each of these mechanisms also may be different. And to try to answer this question, I will present you the initial mass function as a tool to do so. So essentially, the initial mass function tries to count how many stars do we have per each mass bin or luminosity bin. So here we have OB type stars, which are very massive, very bright, but very rare. So we have few of them. And as we go to lower and lower mass objects, we see that these objects are more common. So low mass stars are very common. And then we get into the brown dwarf and planetary mass regime. And this is exactly what we want to investigate. How frequent are these objects? And also this will, I will show at the end that this will be an important parameter to constrain the mechanisms that form this type of objects. Okay, so before doing this, let's move to the second section, in which we will try to see how can we detect these free-floating planets. So I was already introducing you before the cooling evolution of brown dwarf and free-floating planets. So here what you see is the luminosity as a function of age. And we have represented different types of objects: stars, brown dwarf, and planets. Essentially, we see that stars have a period initially where they are still contracting in the pre-main sequence, so they cool down slightly since they are formed. But once they enter in the main sequence and start hydrogen nuclear fusion in an efficient way, their luminosity establishes for many millions or even gigayears. So this is the case of stars. They almost always shine the same until the late stages of stellar evolution, where they become giant stars and explode. On the contrary, what we see for brown dwarf and planets is that since they are born, they always cool down and become fainter and fainter. And this is very important if we want to look for them, because the solution will be always to look for brown dwarf and planets when they are young, because this is the period where they will shine the most. So to look for brown dwarf and free-floating planets, we will look for nearby star-forming regions for this particular reason that I'm saying, and nearby also because these objects are intrinsically very faint. So we will only be capable of observing them in nearby regions. Also, we will try to look them in the infrared, because these objects are very cool. They have very low temperatures, and so their peak of emission is more towards the infrared and not so much in the optical. So these are two important properties. And so one of the techniques to detect free-floating planets directly in the images is using photometry. So here what you are seeing is a color magnitude diagram of different filters in the infrared. So we have J versus J minus H color. This is all in the infrared, as I was saying. And in this diagram, thanks to evolutionary models, we can identify different regions that stars, brown dwarf, and free-floating planets occupy different regions in this diagram. So here, the brightest objects are stars. Then we have the brown dwarf regime and eventually free-floating planets. And here, what this diagram is showing also is that when we have interstellar extinction due to the parent molecular clouds, so these objects also appear sometimes redder than what they actually are. And so sometimes it's difficult to classify them as stars, brown dwarf, or free-floating planets only using this diagram. Then, for this reason, it's very important to have a spectroscopic confirmation. So once we have a few candidates of free-floating planets, we need to obtain spectra, even if it's a low-resolution spectra. One of the things that already are very useful is to study the continuum emission of these objects, because, for instance, in the infrared, they have this triangular shape, which is very characteristic of brown dwarf and free-floating planets. And this is a very important test, as I was saying, to confirm objects and discard that they could be more massive objects or even background stars and galaxies that only appear very faint and very red because they are far away and embedded into a molecular cloud. So this is how the first free-floating planets were discovered. Then now what you're seeing is a map of the solar neighborhood where our sun is exactly at the center here. And here we have the galactic center, and we have highlighted here some star-forming regions around the sun. So for instance, you might be familiar with regions like Orion, Taurus, Perseus, Cepheus, Chameleon, Ophiuchus, Corona Australis, Serpens. So all these are very young star-forming regions around the sun at distances of less than 200, 400 parsecs. And nowadays, we have already identified some of these free-floating planets in all these regions. And what this is telling us is that free-floating planets are, in fact, a very common product of star formation. If we only know few of them, it's because they are at the limits of our capacities. So we need every time more sensitive and more high-resolution objects. But these objects must be very common in the solar neighborhood and probably in the universe. And now I would like to focus in one of these regions because I have been particularly working in this area myself. And this, what you're seeing now, is the region of Ophiuchus and Upper Scorpius. So here we have Ophiuchus, where you see all these dense molecular clouds. This area is very young. It has an age of between 1 and 3 million years. And there is still star formation ongoing. So this is good news because the brown dwarf and free-floating planets are still very bright, but at the same time we have a lot of gas and dust, as you can see in this image, which the same molecular cloud that formed the objects is also hindering us from seeing them. At the same time, next to it, we have the area of Upper Scorpius, which is slightly older. It has an age between 5 and 10 million years. In this case, the brown dwarf and free-floating planets already started to diminish their light, but also the molecular cloud has mostly vanished. And then this facilitates a lot the identification of this type of objects. So this is what I was trying to do during my PhD, and you have to know that in this region, we analyzed around 74,000 images over the past 20 years. And this is an important information that this data were taking over a time span of 20 years, because in this case, we didn't only use the information on the color magnitude diagram that I was presenting to you, but we also used the information on the motion. And we tried to measure the proper motion of all the stars in this image to try to identify the stars, brown dwarf and planets that move together with respect to all the background stars, which have random or very small motions. I will get to more details in this in a moment. So by analyzing all these images, we were able to discover this large family of free-floating planets, which counts on around 100 free-floating planets over 3,500 members in this area. So all these red circles that you see in this image are the free-floating planets. And as I was mentioning, to make this discovery, what we did is combine the information on the proper motions and the photometry. So essentially, we look for objects that move together, these red stars in this diagram. So stars, brown dwarf and free-floating planets that move together and move differently from the majority of field stars, background stars, which have very small motions or random motions around zero. So this on one side, and also on the other side, we looked for members that follow this isochrone of objects around 3 to 10 million years. And combining this information is how we could discover this family. Now, I'm going to zoom in this region, and I am showing you one of these images that we analyzed. And this image contains a very special object. Exactly at the center of the image, there is an object of 8 times the mass of our Jupiter. So you can try to guess which is it. I'm not sure in the room the quality of the projector is going to be enough, but since this presentation I think will be online later, you can try to have a look on a good screen, and you should try to find an object that is very faint and at the same time very red. And this is exactly that one. This is one of these free-floating planets of only 8 times the mass of our Jupiter. And what's really interesting about this object is that, so our survey was not only, again, capable of identifying and measuring the brightness in different filters, but also measuring the motion of this object in the sky over some years. But as I said, this only brings us candidates of free-floating planets, and to be sure that they are indeed young planets and not background stars that are reddened due to interstellar extinction, we need spectroscopy. So spectroscopy is great to confirm these objects, but at the same time is very expensive. So you have to imagine for each of these objects, it takes between 1 and 2 hours of integration time to obtain a single spectra, a single low-resolution spectra. So it is impossible to do this for these 100 of objects. So what we did is to select a random sample of our free-floating planets, which is this one in this color magnitude diagram, and the objects which have a star were observed with these 2 spectrographs, EMIR at the GTC and SWIMS at Subaru. And the good news is that out of these 17 targets, we could confirm 16 as ultra-cool dwarf objects between 4 and 13 times the mass of our Jupiter. This is a really high success rate. And since our initial sample was random, so we have reasons to believe that the family of free-floating planets that we published, in fact, has a very low contamination rate. And then also it's important to say that all these objects are interesting targets to be followed up in other facilities like ALMA or the recent JWST. And these other facilities will allow us to learn more about their disks fraction, about their atmospheres and what is the composition. And all these tests will also help us to characterize better this type of objects and learn also about their origin. Also for completeness, so direct imaging is not the only way of detecting free-floating planets. Many of them have also been detected through microlensing. This is really not my specialty. I know that you have many experts here in Warsaw, but maybe just for completeness, these free-floating planets can also be detected by microlensing, which essentially means that when we observe a background star, and eventually one of these planets aligns on the same line of sight between us and this background star, we see that the light of the star increases over a very short period of time. And this gives us information on the mass of this object that is in between us and the star. And this way, it has been possible to identify many of these free-floating planets. And what's even more exciting, we have been able to detect even terrestrial free-floating planets. So this is a limitation we have from direct imaging, because the current sensitivities of our telescopes don't allow us to detect such low mass objects, but it is possible with microlensing, meaning that for sure these objects must be out there, and we just need better and better telescopes to be able to detect them directly in our images. Okay. And with this, I think we can move to the third block of the talk. And now I will be trying to put all the information that we have discussed together to try to answer what is the origin of these free-floating planets, or what's the same, which is the mechanism that form these free-floating planets. To do so, I will use this sample that I have just presented to you to discuss this question. And the reason is that this is the largest family of free-floating planets that were born together, that we know. Because in the other nearby star-forming regions, the planets that we have identified in other nearby star-forming regions, the samples are typically smaller. And with microlensing techniques, the problem is that the properties of planets that we know are not homogeneous, and they were not born together. So for the moment, this is why I will be using this sample. And the first thing that we can do is obtain the magnitude distribution. This magnitude distribution is a very important tool because it's a direct product from observations. It only depends on the census of stars, brown dwarfs, and free-floating planets that we have obtained. But once we have the members, the magnitudes are directly there. So we can simply count how many objects we have per magnitude bin. And here we have high mass stars. We see again, low mass stars are very common. And at brown dwarf masses, this luminosity distribution starts to decrease. And what we found really interesting is this dip at planetary masses. And one of the possible hypotheses to explain this dip is that this could maybe represent the frontier or the boundary between different formation mechanisms. However, this is only an hypothesis for the moment, and we need more samples and more models to confirm this hypothesis. So as I was saying, that the magnitude distribution is very useful because it doesn't involve any modeling. It's a direct product from observations, but at the same time, it has an important drawback, and this is that brown dwarf and free-floating planets change a lot their brightness over time. So they cool down very rapidly. So we cannot compare the magnitude distribution directly in different regions where the objects are at different evolutionary stages. For this, we need the mass distribution. However, going from magnitudes to masses is not absolutely straightforward. And we need to rely on evolutionary models. Evolutionary models, on one hand, depend a bit on the internal physics that was used to produce them. And also, they change a lot for substellar objects. Then they change a lot very rapidly with age. And then it's, for instance, you are seeing here this red line is the evolutionary model at 1 million years, and the blue line is the evolutionary model at 10 million years. And we see that only within these 10 million year times, stars have cooled down 4 magnitude. So meaning that if we don't know the age of these objects, it's very complicated to distinguish between a 0.1 0.01 solar mass object and a clearly more massive one. So here, either we know very good the age of our sample, or the age uncertainty is going to be translated into a mass uncertainty into the mass function. Anyways, assuming these evolutionary models, one can compute individual masses for individual objects, and then we can go from this magnitude distribution that I have just introduced to you into the mass function. Right? Here, the uncertainties on the mass function are also related to the uncertainties into the age. I said that in this star-forming region that I am showing to you. So we have objects that are both around 3 million years and around 10 million years, and this is the uncertainty also that we have in the mass function. Still, even considering these caveats, this is one of the most precise and accurate mass functions that we have to date. And therefore, we can try to analyze and see what information can we obtain from this. First, just let me tell you that here at high masses, this mass function is similar to a salpeter slope, as it has been found in many other regions. So here there was no surprise. And the other interesting thing to recall is that the fraction of free-floating planets is rather large. Again, because we know that these objects are frequent in our galaxy. And it's important to remind you that here we will be missing some of the sources. So we know that our sample of free-floating planets is not complete, but a lower limit, because there is a lot of extinction, and in this area, it's likely that we are missing objects. And at the same time, we tested that the contamination rate of our sample is very low. So this is only a lower limit on the true number of free-floating planets that we are expecting in this region. Then what we can do is compare these observations with the results of simulations to try to interpret the agreement or the differences. And this is exactly what I will show you in the next slide, where here we are seeing again in red the same mass function I presented in the previous slide. And now the two white functions come from numerical simulations. These numerical simulations, well, the first thing that we can already see at the beginning is that there is a more or less good agreement in the stellar and high mass brown dwarf regime. However, for free-floating planets, we see that we observe many more of such objects than what these simulations predict. And here, let me tell you that these simulations form free-floating planets mainly by core collapse. That's to say, similar to low-mass stars. So comparing these observations of free-floating planets to these simulations, what we could see is that some of these free-floating planets were likely formed like low-mass stars, especially the most massive ones, but this mechanism could probably not explain the formation of very low-mass objects. So what is the origin of all these very low-mass free-floating planets? Well, then we have to look into the other scenario, where free-floating planets can form similar to planetary mass objects that they can form similar to exoplanets that later are ejected from the planetary system. And here, this is not a complicated equation. This is similar, only telling us that the observed fraction of free-floating planets, this would come exactly from this plot that I'm showing here. So this fraction of free-floating planets that we observe in this region has to be similar to the fraction of stars that host giant planets. This we get it from statistics of exoplanetary systems times the fraction of such exoplanetary systems that have very eccentric orbits. which eventually can be ejected. So these values come again from exoplanetary surveys and also from simulations on how these exoplanets can become unstable and be ejected. But plugging all these numbers, comparing all these numbers to our observed mass distribution, we again found that a significant fraction from our sample could indeed have formed by this mechanism. Here, I think the point is not, so currently with the information that we have, we can not constrain very well the fraction by which different mechanisms form. But I think here the main point is to show that the two formation mechanisms are important, and indeed we need more information to finally tell the two of them apart, but they need to be incorporated both in the future numerical simulations. And then before finishing, I would like to mention a very recent study that has been published in Archive recently. You may have heard of this because they also did a very nice press release. And in this case, they have found not only free-floating planets, but free-floating planets that apparently come in binaries. So they come in pairs. This is what you see in this image. There is not one of such objects, but two. This is super interesting and super exciting because this is something that we did not see in Upper Scorpius, and also it poses some challenges into the formation of these objects, especially because a binary pair is unlikely to survive to an ejection process. And I was just saying that ejection from planetary system maybe is the most likely process to form especially low mass free-floating planets. So this is indeed a puzzle that we will have to see. Maybe only let me add a word of caution here, because these objects are extremely embedded into their parent molecular cloud, and the amount of extinction that they have is extremely high. So it will be really important first to confirm the mass of these objects and to confirm that they are indeed planetary mass objects before we can analyze further the conclusions. But if this is confirmed, this is going to be a very, very exciting result. And so more of the same, the authors of the study also reported the fraction of binaries as a function of mass. So this blue crosses, this is what we know up to now. So we know that very massive stars are often formed in binary or multiple systems, and as we go to lower and lower mass objects, the binary frequency decreases. And this was interpreted the fact that brown dwarf and free-floating planets every time had less and less fraction of binary pairs, was interpreted in the sense that these objects maybe started to form in a different mechanism. But if, again, this fraction increases, this maybe tells us that the same mechanism that was acting for low mass stars could be acting at such low mass objects. We will have to see. And finally, also for completeness, another parameter that gives us a lot of information about the formation of these objects is the disk fraction. So stars, we know that stars are formed with a disk surrounding the star. So the presence or not of such circumstellar disks around brown dwarf and free-floating planets is also telling something about their formation mechanism. If we see disks similar to what we see for stars, this is going to tell us that probably they formed similar to stars, while if we see that brown dwarf and free-floating planets have no disks, or the disks have very different properties. They are very small or they are truncated. Maybe this is going to tell us that the formation mechanism was very different. So here in this image that I'm showing you, you see the disk fraction as a function of spectral type. And here we have high mass stars, and we are going slowly to lower mass stars. And in this study, they could only identify disks for objects more massive than 10 times the mass of our Jupiter. So these authors were suggesting maybe this is the limit of objects that form similar to low mass stars, and the rest would form differently. In this other diagram, what you're seeing is the size of the disk, well, in fact, the mass of the disk as a function of the mass of the object. And when we go to lower and lower mass objects here to the left, we see that every time the disks are smaller, but following a continuous relation. So while this is continuous, maybe these objects also form similar to stars. But all this to say that this is also the presence or not of disks is another important property to investigate the origin of these objects. And with this, I move to my conclusions, and I would like to finish with these 3 takeaway messages. So first of all, free-floating planets are a common output of star formation, and we have seen this both from direct imaging studies and also from microlensing studies. Then the mass function, but also the binary fraction and the disk fraction are excellent tools to study the origin of these free-floating planets. And finally, we will need still more efforts to combine observations and simulations to learn more about the process that forms this type of objects. So thank you very much for your attention, and I'm happy to take any questions that you may have.
Before we go into questions, I would like to note that I was sitting in the first row and I've seen the red dot in the middle of the image.
Cool.
If somebody here in the room has not seen it, you can sit closer to the front row next time.
Yeah.
Okay, questions?
So I have a question about the extinction. You showed the JWST images where they discovered some binary planet candidates, but you said that these candidates are quite uncertain because they are embedded in a large dust cloud, and obviously there is a lot of stuff between us and these objects. So my question is about the extinction to the objects that you discussed and you studied. How did you estimate the extinction, and what is its impact on the mass estimates that you have?
That's a very good question. Let me go to one of the... Okay, here. Do you see my screen, or do I have to maybe do this? You see my screen, right? Again? Yes? Okay. I'll assume yes. If you don't see it, please let me know. Okay, so the extinction. So in principle, the extinction of the objects that we found, especially in the brown dwarf and free-floating planet regime, is rather light and rather small, sorry. And we can see this already in this color magnitude diagram, where, for instance, stars, we do see many objects that sit on the right-hand side of the isochrones, while for brown dwarf and free-floating planets, we are probably missing all these objects. And this is why I say that we think that our fraction is only a lower limit. The reason why this is happening is that for high mass stars, we are using Gaia, and Gaia has not only proper motions but also parallaxes. So these objects are very easily identified only with astrometry. So photometry always helps, but astrometry is already very useful to identify all these objects. Whilst here, we only rely on ground-based images, and then we have proper motions indeed, but this has to be combined with many color magnitude diagrams. And the way our algorithm works is it looks for stars that are close to the empirical isochron. So we define a sequence where our members are sitting, and the algorithm looks for objects that are nearby this isochron. So for definition, we are going to miss most of these very red embedded objects. Yeah, then also it's true that in some cases the extinction can be a bit higher. So for instance, here you see some objects sitting exactly on top of the cloud. In this case, these could be in fact brown dwarf and not free-floating planets. I would say these I'm a bit less confident, but many and most of them are sitting in regions where the extinction is very low. So I'm quite confident that the extinctions are low in this area, and therefore the masses are accurate. But I hope this answers the question.
I think so. So one more question about the lower right plot. How do you explain the objects that are left to the isochron?
The objects that are left to these ones?
Yeah, here.
Yeah, so here there is probably a bit of contamination.
Yeah, but what kind of objects are these? Like younger stars in this part of the sky that are related to the or unrelated?
No, I think probably these are unrelated. So the reason is that, so we did two independent studies, one using the Gaia astrometry and photometry, and the other using the ground-based astrometry and photometry. So with Gaia, as I was saying, in this area, it's very easy because you have proper motions and parallaxes, and this makes your job very easy. But then some of these objects are also observed with our ground-based images. And then the approach that we took is to combine both lists. So the members that we could find with Gaia and the members we could find with the ground-based images. And I would say most of these are found with the ground-based images, but maybe not with Gaia. So they are essentially just objects that maybe have similar motions, but are older stars and which are unrelated to the region. But this is very focused on this area of the color magnitude diagram. And it's really, so it's visible in the plot, but in terms of number, it's a really small fraction of the members.
So I see we have a question online from Zoom.
Hi, thank you for your presentation. My question is, what is the estimated number of freely floating planets exist in our galaxy?
So that's a complicated question, and it depends. Maybe here you have a better estimate from the microlensing surveys, because what we can say only for imaging, so with imaging surveys, we can only do these studies in very nearby star-forming regions. But this fraction may be different if we focus in a cluster which has a lot of very massive OB stars. So it's a bit hard to extrapolate the fraction that we see in this local bubble to the entire galaxy. So maybe here microlensing surveys for the moment will give you a better estimate.
Okay, thank you.
You're welcome.
That's I can comment that indeed microlensing surveys are discovering very short timescale microlensing events, which may be due to such planetary mass objects. currently, we estimate there is at least one free-floating planet per every star. Probably there are even more, but I would say these numbers are quite uncertain at the moment. We collecting data, but I think there are at least a few free-floating planets per every star in the Milky Way, according to the gravitational mechanics data.
I would just add, we're talking about the objects that are much less massive than Jupiter in that case. These are like Jupiter mass planets. I see you have a question from Tomek Kamiński from Zoom.
Yes. Hello, can you hear me?
Yes.
Yeah, thank you for this beautiful presentation. So this is not my field. My question is going to be really out there. Now with the discovery of the double brown dwarfs, we can think that there may be planets that are even closer to each other. And there may be some tidal interaction, which I guess in principle could have some effect on the cooling rates. So if you have some tidal cycling, you can get a lot of energy from gravitational potential into the internal energy of the components. Is that being considered in the models, the binary, closed binary systems of planets, or big planets with satellites with moons would cool differently than single objects?
That's a very interesting question, but I'm afraid I will not be able to answer because my work is really not so much focused on the modeling side. However, what I would say is that these objects are mainly white binaries, not closed binaries. So I'm not sure what you say would apply.
Yeah, those are probably easier to recognize at the moment. Yeah. All right, thank you.
Thank you.
Any final question, Milena?
Yes, so I have a question regarding to the plot that you are showing right now. So as lower the mass in some mass regime, the higher binarity fraction. So does it mean that we should see, if we go to the very low mass free-floating planets that we can discover via microlensing, we should see binary objects? Can we see any of this Neptune size, or well, probably not Earth size, but at least if we go lower in the mass there?
So I think here the limit they had is around 1 Jupiter mass object. If I remember correctly, this is the lightest object that they could find. However, I would say it will be really interesting to see what microlensing studies have to say here, and also what studies in other regions have to say. So this is really new and really preliminary. So I think, as I said before, first, for me, these objects still need to be confirmed with spectroscopy to discard that they are, so to confirm that they are indeed such low mass objects and not higher mass objects, because then it could easily explain why the binary fraction is so high. But if this result is confirmed, then I think it's going to be really exciting to see how frequent or how rare this result is, because as I was saying, in upper Scorpius, this is not something that we saw. We didn't find any pair of binary objects at these very low mass objects. So yeah, I think this is really new, but will need to be confirmed with spectroscopy and also with other studies in other regions, or exactly with different techniques from microlensing, as you were suggesting.
Okay, thank you once more. And if there are round of applause. Thank you very much.
Okay, and we see each other next week to listen to some astroseismology talk. Thank you very much.
Thank you. Thank you very much.
So, yes.